Mars has stopped responding. Not entirely, not in the way you might think, but enough for every scientist on Earth, with access to telescopes and orbital stations, to feel that something has changed. Something invisible, elusive, but absolutely real passed through the red planet. And now, we are trying to understand exactly what we are observing. Friends, please write in the comments where you are watching us from. What city? What country? Perhaps right now, as you listen to this, you are somewhere beyond the Arctic Circle or at the equator. It is important for us to know that this story unites people across the globe, because what we are about to tell you concerns every one of us. 4 months ago, humanity first detected an object that should not have existed in our solar system. It was not an asteroid or a comet in the usual sense. It was an interstellar interloper, the second confirmed visitor from the depths of space after Oumuamua. It was named 3I Atlas. On July 1 of the current year, an automated asteroid search system recorded a faint streak of light at the edge of the Ursa Major constellation. Initially, it was just another dot, another line in the database, another entry in the catalogue of celestial bodies. But after 48 hours, it became clear that this was an unusual object. The trajectory was erratic, too elongated, too fast. A speed of 42 kilometers per second relative to the Sun is not characteristic of objects born in our system. The gravity of our star cannot accelerate a rock to such magnitudes if it originally belonged to the local cosmic environment. The orbital eccentricity exceeded 1, a mathematical indicator that the object came from somewhere outside, from the interstellar medium, where distances are measured in light years, and time flows on scales inaccessible to human perception. Calculations showed that 3I Atlas began its journey somewhere in the vicinity of a star we cannot even precisely identify. Perhaps it was a red dwarf in the Gemini constellation, perhaps something more distant and colder. For millions of years, this object flew through absolute vacuum, encountering nothing but random atoms of hydrogen and dust particles left after the birth of the galaxy. No light except for distant stars, no heat except for the universe's background radiation, cooled to near absolute zero. Only an endless fall in a direction, once determined long ago by the gravity of a long-dead star or a supernova explosion that tossed this rock like a toy and sent it on an eternal journey. And now it is here, in our system, hurtling through the inner planets, and its trajectory intersects with the orbit of Mars. It does not just pass nearby. It intersects directly at the point where the red planet was located in mid-September. Astronomers began sounding the alarm a week after the discovery, when it became clear that the distance between the object and Mars could be less than 100,000 kilometers. That is cosmic proximity, practically a touch on a planetary scale. But 3I Atlas turned out to be more than just a rock. The first spectral analyses showed something strange. The object was emitting gas, not a classical comet tail, but something more subtle, almost imperceptible. A cloud of particles that trailed behind it for millions of kilometers, so tenuous that it could only be detected using the most sensitive instruments. The composition of this cloud remains a mystery. Initial data suggested the presence of complex organic molecules, water, ice, ammonia, and possibly hydrocarbons. But there were also other lines in the spectrum that did not correspond to any known compound. When the object approached Mars, something happened that no one expected. The particle cloud surrounding the interstellar interloper enveloped the planet. This was not a powerful impact, not a collision in the literal sense. It was a passage through a density of matter so low that on Earth we would call it a vacuum, but on cosmic scales, even a diffuse gas can carry enough energy to alter the atmosphere of an entire planet. Mars, with its thin shell of carbon dioxide and virtually non-existent magnetic field, was defenseless against this invisible flow. The first data came from Martian orbital probes. Spectrometers recorded a sharp spike of unusual molecules in the upper atmosphere. The concentration of certain compounds increased by several orders of magnitude in a matter of hours. These were substances that should never have been there. Radiation detectors showed anomalies. Magnetic field sensors recorded fluctuations that did not correspond to any known models. Rovers on the surface, operating in automated mode, began transmitting strange readings. The ambient temperature fluctuated within limits that did not align with the planet's diurnal cycles. The scientific community paused. Data was analyzed around the clock in laboratories worldwide. Space agencies convened emergency meetings. Telescopes were redirected towards Mars, attempting to capture any changes in its atmosphere, surface, or magnetosphere. But the more information came in, the less understanding there was of what exactly had happened. Each new dataset added questions, not answers. Mars is a planet that was once similar to Earth. 4 billion years ago, rivers flowed there, and oceans stretched for several kilometers in depth. A thick atmosphere protected the surface from cosmic radiation. The climate was wet and warm, like the young Earth in the Archean eon. Perhaps life was emerging there. Simple, microbial, but life in its primal form, capable of adapting and evolving. But then, something happened. The planet's core cooled, the magnetic field disappeared, and the solar wind began stripping away the atmosphere layer by layer. Water evaporated or froze beneath the surface. Mars turned into a cold desert, where the average temperature hovers around -60 degrees Celsius, and the pressure is so low that liquid water cannot exist on the surface. Now, this dead planet has encountered material from another star system. This is not simply cosmic dust that constantly bombards all bodies in the solar system. This is material that formed under conditions different from our own. Its chemical composition was determined by another star, other planets, and other processes that occurred in the protoplanetary disk, where 3I Atlas was once born. If organic molecules are present there, as the spectral analysis hints, then this is organic matter that has never contacted Earth's biochemistry, never been subjected to the evolutionary pressure familiar to us from the history of life on Earth. Imagine for a moment you are standing on a Martian plane in a spacesuit, protecting you from the deadly environment, and looking up at the sky. It is pinkish-orange, due to the suspension of fine dust that never completely settles. The sun shines about half as brightly as on Earth. Everything around is covered in reddish-brown regolith, the Martian soil, consisting of iron oxides, basaltic rocks, and traces of ancient volcanoes. The temperature drops so quickly after sunset that you can see carbon dioxide precipitating as frost on the rocks. The silence is absolute. The atmosphere is too thin to transmit sound over long distances. And suddenly, in this sky, something appears, invisible to the eye, imperceptible, even to instruments in real time, yet present. A cloud of interstellar particles passes through the atmosphere, through you, through the planet itself, leaving behind changes that we are only beginning to comprehend. What is happening to the atmosphere of Mars right now? The data is contradictory. One of the orbital spectrometers recorded an increase in the concentration of methane, a gas almost always associated with biological activity on Earth, although it can also be formed through geological processes. But methane on Mars is always a mystery, because it is quickly destroyed by the sun's ultraviolet radiation. And if its concentration is rising, it means there is a source somewhere constantly replenishing its supply. Until now, no one could precisely determine where this gas comes from subsurface reservoirs, from microbial life hidden deep within, or from chemical reactions in the planet's mantle. Now, the concentration of methane has increased several-fold in a short period after the 3I Atlas cloud passed. This could mean that the particles of the interstellar object catalyzed some processes in the atmosphere or on the surface. Perhaps they reacted with the minerals in the Martian soil, releasing trapped gas. Perhaps they brought with them compounds that, upon contact with carbon dioxide and water vapor, began synthesizing new molecules. Or, and this is a thought that even the boldest astrobiologists are afraid to voice, perhaps the cloud contained something that activated or awakened something already existing on Mars. The Perseverance rover, located in the Jezero crater, an ancient lake that dried up billions of years ago, began transmitting strange data. A few days after the event, its cameras captured changes in the color of the surrounding soil in one area. Initially, this was considered a calibration error or a trick of the light, but the analysis showed that the spectral signature of the rock had indeed changed, as if some chemical process had passed over the surface, transforming minerals into new compounds. The rover's robotic arm took a sample, and the analyzer showed the presence of molecules that were not there during previous measurements at the same spot weeks earlier. Meanwhile, orbital probes recorded the appearance of faint anomalies in the ionosphere, the upper layer of the atmosphere, where solar radiation ionizes gases. The density of charged particles fluctuated unusually, creating local disturbances that did not correspond to either solar activity or magnetic storms. It was as if the Martian atmosphere was reacting to something invisible, some influence that our instruments cannot yet register directly. Scientific papers began appearing with unprecedented speed. Teams of researchers worldwide worked in a 24-hour monitoring mode, exchanging data, building models, and trying to predict what might happen next. One of the largest astrophysical institutes published a preliminary report suggesting that the 3I Atlas particle cloud could have introduced up to several million tons of organic material into the Martian atmosphere, a number that sounds enormous to human perception, yet negligible on a planetary scale. Nevertheless, even this amount of substance, distributed in the upper atmosphere and on the surface, could trigger a chain of reactions whose consequences are impossible to predict without long-term observations. Another group of scientists proposed the hypothesis that the particles might have contained complex hydrocarbons and amino acids, the building blocks of life. If so, Mars received a substantial dose of organic matter for the first time in billions of years, and organic matter that formed under entirely different conditions. On Earth, similar molecules are constantly being destroyed and recreated in the cycle of biological and geochemical processes. On Mars, there is no such cycle. Organic matter can be preserved there for millions of years, slowly changing under the influence of radiation and oxidative processes. Now, new organic matter from another star system has mixed with the Martian environment. No model can predict what will happen next. The most troubling thing is the silence. Not complete, of course. Data continues to flow. Rovers are working. Orbital stations are functioning. But something has changed in the nature of the information. Specialists working with Martian missions speak of a strange feeling that is difficult to express in words. The planet is not reacting as it did before. Instrument readings fluctuate within acceptable error margins, but the very structure of these fluctuations has changed. It is as if Mars has awakened from a long sleep and is trying to adapt to something new, something that has not been there for the last 4 billion years. The story of 3I Atlas did not begin in July, when telescopes discovered it. It began immeasurably long ago, when a star, whose name we will never know, exploded as a supernova, or simply ejected a cloud of gas and dust from which planetesimals, the embryos of planets, formed. One of these rocky fragments, perhaps the size of a small mountain, gained enough speed to escape the gravitational pull of its star. Maybe it was just a fortunate trajectory, a random combination of gravitational influences from several giant planets that flung the rock into an escaping orbit. Perhaps the explosion of a nearby supernova gave it the necessary impulse. In any case, this object began its journey through the galaxy long before life appeared on Earth, perhaps even before the solar system itself formed. Interstellar space is not a vacuum in the absolute sense. There is gas, mainly hydrogen and helium, left over from the Big Bang and the subsequent formation of stars. There is dust, microscopic grains of silicates, carbon, and ice, formed in the atmospheres of dying stars and ejected into space. There are cosmic rays, streams of high-energy particles accelerated by supernova explosions to speeds close to that of light. And there is darkness, so profound that the light of the closest stars provides illumination billions of times weaker than moonlight on Earth. In this environment, 3I Atlas flew, gradually covered by a thin layer of interstellar dust, bombarded by cosmic rays, slowly changing its composition, under the influence of processes encountered nowhere but in deep space. When the object entered our solar system, it carried all this history imprinted in its composition. Every atom on its surface holds information about the path it traveled. The isotopic composition differs from the local material. The first spectral analyses immediately showed this. The ratio of light to heavy elements indicates that the material formed in a protoplanetary disk with different characteristics, perhaps around a star that was richer in heavy elements than our Sun, or conversely, poorer. This means that all the chemistry, all the physics of this object carry the imprint of an alien star system, an alien history of planetary formation, and alien conditions under which matter organizes into structures. And now, this foreign material has mixed with Mars. The planet, which existed in isolation for billions of years, has received an influx of matter from outside, not from the asteroid belt, not from comets born in the Oort cloud at the edge of our system, but from true interstellar space. It is as if an isolated ecosystem, existing for millions of years without external intervention, were suddenly entered by organisms from another ecosystem, with different biochemistry and different rules of survival. The result is impossible to predict. The system may adapt the new players, it may reject them, or it may undergo cascade changes that transform it beyond recognition. The latest data from Mars indicate that the processes are not stopping. The concentration of anomalous compounds in the atmosphere continues to slowly increase. This is not explosive growth, not a catastrophe in the usual sense. It is a slow, almost imperceptible change that may stretch over months or years. But the trend is obvious, and it does not match any previous model of Martian atmospheric dynamics. Something has been initiated. A process has begun and continues to evolve, fueled by the Sun's energy, the planet's chemistry, and perhaps the substances brought by the interstellar interloper. Scientists are debating whether this is a threat or an opportunity. On the one hand, any uncontrolled change on a planet we are studying for future colonization is alarming. If the Martian atmosphere becomes even more unpredictable, if the chemical composition of the surface changes in an unknown way, it will complicate all plans for the planet's development. On the other hand, perhaps this is a unique natural experiment that shows us how planets can evolve under external influence. Perhaps we are witnessing something that has happened billions of times in the galaxy's history, the migration of organic material between star systems, a process that might underpin the spread of life in the universe. The panspermia theory, the idea that life could have originated in one place and spread throughout space via comets and asteroids, has been discussed for more than a century. But until now, it was only a hypothesis, a beautiful idea without direct proof. Now, for the first time, we are observing an interstellar object directly interacting with a planet, potentially transferring organic material across light years. If analysis shows that complex organic molecules, or even something more interesting, spores, RNA molecules, any structures capable of self-organization, were indeed present in the 3I Atlas particle cloud, it will overturn our understanding of how complexity spreads in the universe. But there is a darker side to this story. What if the cloud contained not just organic matter, but something capable of activity in Martian conditions? Spores of Earth microorganisms can survive in space for years, protected by thick cell walls from radiation and vacuum. What if life from another star system has evolved mechanisms that allow it to travel between worlds, using comets and asteroids as vehicles? This sounds like science fiction, but physics does not forbid such a possibility. Microbes are incredibly adaptable. On Earth, they are found in the most extreme environments, from volcanic vents to radioactive waste, from Antarctic ice to acidic lakes. Who is to say that life from another system cannot be even more resilient? Mars is now a natural laboratory where a cosmic-scale experiment is unfolding. We cannot control it. We can only observe and try to understand. Each day brings new data. Each week, new anomalies appear in instrument readings. The scientific community is divided into those who consider what is happening an interesting but harmless natural fluctuation, and those who see in it the beginning of something greater, a process that could change Mars in ways we cannot yet predict. The most important thing is time. Mars changes slowly. Geological and atmospheric processes there are stretched over thousands and millions of years. But if the impact of 3I Atlas has indeed triggered some cascade of reactions, we may see noticeable changes in the coming months or years. This is an unprecedentedly short period by the standards of planetology. Usually, we study planets in a static state, observing the results of processes that ended millions of years ago. Now we have a chance to see the dynamics, how a planet reacts to external influence in real time, how its atmosphere and surface adapt to new conditions. 3I Atlas, meanwhile, continues its journey through the inner part of the solar system. Its trajectory is calculated. It will pass near Earth's orbit, but at a safe distance, then dive towards the Sun, heat up, perhaps partially disintegrate from thermal stresses, and exit back onto a hyperbolic trajectory that will carry it away from our system. In a few years, it will be in interstellar space again, continuing its eternal flight to the next star, which it may reach in hundreds of thousands of years. But the mark it left on Mars will remain, and this mark may tell us more about the nature of the universe than thousands of books and theories. Now, as you listen to these lines, scientific institutes worldwide continue to analyze the data. Telescopes monitor Mars around the clock. Rovers are taking new samples of soil and atmosphere. Satellites in orbit are scanning the surface in different spectral ranges, looking for temperature anomalies, chemical changes, and any signs that the planet continues to evolve under the influence of interstellar matter. Each new piece of information adds details to the picture, but the overall picture remains incomplete for now. We see pieces of the mosaic, but cannot put them together into a whole, because we lack the key understanding of exactly what the 3I Atlas particle cloud represents and what processes it is capable of initiating in the Martian environment. Humanity stands at the threshold of a discovery that could change our place in the universe. If we confirm that interstellar objects are capable of carrying complex organic matter or even life between star systems, it will mean that space is not as isolated as we thought. The galaxy may be permeated by a network of chemical and possibly biological connections, where matter and information flow from star to star, from planet to planet, creating a unified ecosystem on scales that surpass imagination. We will no longer be lonely islands in the void. We will become part of a process that has lasted billions of years and encompasses the entire visible universe. But for now, we can only observe and wait. Mars does not give definitive answers. It is silent, slowly changing under an invisible influence, and this silence is filled with the tension of anticipation. What will happen next? What other anomalies will the instruments detect? What new data will force scientists to revise all their theories? The red planet, which seemed dead and predictable, has suddenly become a mystery demanding a solution, and that solution could change everything. The first signs that the situation was moving beyond the scope of ordinary scientific observations appeared in the third week after the cloud passed. The European Space Agency published data from its orbital probe, and this data caused a wave of discussion that quickly crossed the boundaries of the narrow scientific community. On the surface of Mars, in the Utopia Planitia region, a huge lowland in the northern hemisphere of the planet, an anomaly appeared. Neither a meteorite crater, nor a dust storm, nor seasonal changes in the surface albedo. This was something else. An area, approximately 20 kilometers across, began to exhibit unusual spectral characteristics in the infrared range. The temperature of this area was several degrees higher than the surrounding terrain. A local temperature increase is not unique in itself. Microclimatic fluctuations constantly occur on Mars, related to soil composition, the angle of incident sunlight, and the thermal conductivity of the rocks. But in this case, the anomaly was persistent. It did not disappear at night, when the temperature on the planet drops to -100 degrees Celsius. It did not change its intensity depending on the sun's position. It was as if an internal heat source was operating beneath the surface, independent of external conditions. A team of planetologists from the California Institute of Technology spent several days checking all possible technical errors. They recalibrated the sensors, compared the data with other orbital probes, and constructed thermal maps of the entire region for the past 5 years to rule out the possibility that it was simply an area with unusual geological properties that had previously gone unnoticed. But the result remained the same. The anomaly was real. It appeared after the 3I Atlas cloud passed, and it was not going to disappear. The most interesting part began when a high-resolution camera from an orbital reconnaissance satellite was aimed at the area. The images showed changes on the surface, subtle, barely noticeable, but definitely present. The soil in the center of the anomalous zone looked darker than it had weeks earlier. The surface texture had changed. Microstructures appeared, resembling cracks or channels, but too regular to be the result of simple thermal expansion or erosion. Some researchers cautiously suggested that this could be the result of subsurface ice sublimation, a process in which frozen water transitions directly to a gaseous state, bypassing the liquid phase, creating voids and cracks in the soil. But the math did not add up. Such large-scale sublimation requires a powerful energy source, either a sharp rise in temperature or a change in pressure. There has been no volcanic activity on Mars for billions of years. The planet's core is cold, and tectonic processes ceased long ago. Where does the energy come from to heat a patch of soil the size of a small city? The only reasonable answer is chemical reactions. Something in the composition of the Martian regolith began reacting with substances brought by the interstellar object's cloud, and this reaction is exothermic. It releases heat. On Earth, we know of many exothermic processes: the combustion of organic matter, the oxidation of metals, and certain biochemical reactions. All of them release energy in the form of heat. But Martian soil was considered chemically inert. Yes, It contains iron oxides, sulfates, and perchlorates, compounds capable of reacting. But over billions of years, most possible reactions have already occurred, and the planet's surface has reached a kind of chemical equilibrium. Now that equilibrium is disrupted. New molecules from the interstellar cloud are acting as catalysts or reactants, triggering processes that have not happened on Mars since its youth. The scientific community split into several camps. The conservative wing insisted that all observed phenomena could be explained within the framework of known planetology. It just requires more time and data to build the correct model. A group of more radical researchers suggested that we are witnessing the beginning of a massive transformation of the Martian surface, a process that may stretch over decades, but is already showing signs of inevitability. And there was a third group, the smallest but the most intriguing. Those who believed that the explanation might lie outside of pure geochemistry. They spoke of the possibility of biological activity. The word life, in the context of Mars, has always evoked conflicting emotions. On the one hand, it is a planet that once had all the conditions for the emergence and development of primitive organisms. On the other hand, in half a century of intensive research, we have not found a single convincing proof of the existence of even microbial life. Viking in the 1970s conducted biological experiments, whose results still cause debate. Rovers have analyzed thousands of soil samples, searching for organic molecules, traces of metabolism, and any chemical signatures that might indicate the presence of living organisms. The results were ambiguous. Organic matter is present, but it may have a non-biological origin. Methane appears and disappears, but its source is unclear. Now, the situation has changed. For the first time in the history of Martian research, the planet has received an external impact, whose scale we are only beginning to comprehend. If life once existed there, even deep beneath the surface, in protected niches, in a state of anabiosis or minimal activity, the new chemical compounds from the 3I Atlas cloud could have become a stimulus for awakening. Or, even more dramatically, the cloud might have brought spores or other forms of resilient biological structures from its native star system. The idea of panspermia has ceased to be an abstract theory. It has turned into a hypothesis that needs to be tested immediately. A group of astrobiologists from the Massachusetts Institute of Technology proposed an emergency mission, redirect one of the rovers to the anomaly zone to take samples and conduct a detailed analysis. The problem is that the nearest operational rover is several thousand kilometers from Utopia Planitia. Even at a maximum speed of about 200 meters per day, the journey will take years. The alternative is to wait for the next mission, which is planned for several years from now, and include the investigation of the anomalous zone in its objectives. But time is working against us. The processes on Mars are developing now, in real time, and every week of delay means losing a unique opportunity to record the early stage of whatever it is. Meanwhile, data continued to flow, and each new set of information added more mysteries. Atmospheric analysis showed the appearance of molecules that should not have been in the Martian air. These were complex organic compounds, polycyclic aromatic hydrocarbons, furan structures, and possibly even amino acid precursors. On Earth, such molecules are formed as a result of pyrolysis, the thermal decomposition of organic matter at high temperatures. But Mars has no forest fires or industrial emissions. The only reasonable explanation: these molecules either arrived with the 3I Atlas cloud or are being synthesized, now on the surface, as a result of some processes initiated by the interstellar matter. The chemical composition of the new material began to clarify thanks to spectral analysis. The cloud contained not only organic molecules, but also minerals, silicates, oxides, and possibly metal particles. The isotopic composition of these minerals differed from both Martian and Earth materials, direct proof of their extraterrestrial origin from another star system. But the most intriguing discovery was water, not in the form of ice, as on comets in our system, but as hydrated minerals, where water molecules are embedded in the crystal lattice. This suggested that the material formed under conditions where liquid water was present, perhaps on a planet's surface or deep within a large celestial body. Imagine a planet orbiting a distant star. Perhaps it was a super-Earth, a planet with several times the mass of our own, with a dense atmosphere and deep oceans. Perhaps rain fell there, rivers flowed, and geological processes similar to Earth's occurred. Minerals formed under these conditions. Organic molecules went through complex cycles of transformation. Perhaps life arose. Then something happened. A collision with an asteroid, a gravitational disturbance from a passing star. Some catastrophic event ejected fragments of this world into space. One of the fragments flew for millions of years until it reached our system, and now its material has mixed with Martian soil, bringing the memory of that long-vanished planet. The philosophical weight of this idea is hard to overstate. We always thought of star systems as isolated islands in space. Each star lives its own life. The planets around it evolve independently, and there is no connection between the systems except for light traveling for millennia. But 3I Atlas shows that this is not the case. Matter flows from star to star, carrying information about its origin. Perhaps every planet in the galaxy contains fragments of many other worlds, like museums where exhibits from all over the area are collected. We are not alone, even chemically. The elements we are made of could have traveled through space, visiting dozens of star systems before reaching Earth. Observations of the Martian atmosphere revealed another oddity. The concentration of anomalous molecules was heterogeneous. In some regions, it was higher, in others, lower. This did not correspond to a model of uniform substance distribution after the cloud passed. If the cloud had simply dissipated in the atmosphere, the concentration should have leveled out due to diffusion and atmospheric currents. But the maps showed hotspots of elevated concentration that remained stable for weeks, as if something was locally retaining or producing these molecules. One hypothesis suggested that the particles from the cloud settled on the surface and are now slowly releasing volatile compounds under the influence of solar radiation. Ultraviolet light on Mars is more intense than on Earth. Due to the lack of an ozone layer, it is capable of destroying complex molecules, but can also trigger photochemical reactions that synthesize new compounds. If the interstellar material contained organic matter protected by a mineral shell, this organic matter could now be gradually released, reacting with the atmosphere, creating decomposition products that we are observing. Another hypothesis was more radical. What if we are not just seeing chemistry, but biochemistry? What if structures capable of metabolism in Martian conditions were present in the cloud? On Earth, there are extremophiles, organisms that live at sub-zero temperatures, in acidic or alkaline environments, under enormous pressure, or in a vacuum. Some Earth bacteria are capable of entering a state of cryptobiosis, a complete halt of metabolism, and surviving in this state for decades, only to revive when conditions are favorable. Who is to say that life from another star system cannot possess even more astonishing adaptations? The debate between chemists and biologists intensified daily. Chemists pointed out that all observed processes could be explained without invoking biology, simply exotic chemistry in unusual conditions. Biologists countered that some patterns in the data, the stability of the concentration hotspots, and the cyclical nature of fluctuations in atmospheric readings resembled metabolic activity. Neither side could present irrefutable evidence, because that would require direct samples from the anomaly zone, and those were unobtainable in the near future. In this situation, the idea of using artificial intelligence, AI, for data analysis was born. A team of machine learning specialists from several universities created a neural network trained on all available data about Martian atmosphere, geochemistry, and climatology for the past 50 years. Then they fed this system the new data obtained after the cloud passed and asked it to find patterns that did not fit known models. The result was unexpected. The AI identified several areas on Mars where a combination of factors, temperature anomalies, atmospheric composition, and surface spectral characteristics indicated the presence of active processes that had not been observed before. The most intriguing finding was that these areas were not random. They clustered in regions where, according to geological data, ancient lakes or rivers once existed. This could be a coincidence, but it could also indicate that the processes initiated by the 3I Atlas cloud are developing more intensely, where traces of ancient water-hydrated minerals, salts, and organic deposits have been preserved in the soil. It was as if the new material found a nutrient medium in these places, something that allowed the reactions to proceed faster and more efficiently. The discussion moved into the public sphere. Scientific journals published articles with mutually exclusive conclusions. Conferences gathered hundreds of specialists who debated the nature of the observed phenomena. Social media filled with discussions, from serious data analyses to fantastical assumptions about aliens and extraterrestrial infection. Space agencies issued cautious statements, urging people to wait for additional data before making final conclusions. But nervousness was growing. For the first time in history, humanity was observing changes on another planet caused by interstellar matter. We did not know how this would end. Meanwhile, another line of research was developing, the study of 3I Atlas itself. The object had passed Mars and was approaching the inner part of the system. Its brightness had increased slightly, a sign that the object was heating up as it approached the Sun and emitting more gas and dust. Spectral analysis of this new emission provided important information. It turned out that the gas composition had changed compared to what was observed a month ago. While simple molecules, water, carbon dioxide, and ammonia dominated before, more complex compounds had now appeared. This suggested that as it heated, substances were being released from the object's interior that had been frozen deep inside since its formation. The surface temperature of 3I Atlas had risen from -200 degrees Celsius to approximately -100 degrees Celsius. This is enough for ice to sublimate more actively, for some frozen organic compounds to transition into the gas phase. If we use an Earth analogy, it is as if an ancient glacier began to melt, releasing everything that had been locked within it for millions of years. Only in this case, the glacier formed not on Earth, but around another star, under conditions that we can only speculate about. A group of scientists proposed an ambitious plan to attempt to obtain a sample of the substance directly from the 3I Atlas cloud. Technically, this is possible. There are mission concepts for sampling the tails of comets. But the problem is time. Preparing such a mission requires years, and the object is already moving towards perihelion, the point of closest approach to the Sun, and will begin to move away, gaining speed, in a few months. The missed moment cannot be recovered. The next interstellar object may fly through our system in a decade, or it may never pass so close to the planets. In the scientific community, there was a sense of missed opportunity. We knew about the approach of 3I Atlas for several months, but did not fully realize the significance of the event. No one expected the particle cloud to have a noticeable effect on Mars. It was assumed that the object would simply fly by. Astronomers would take measurements, publish articles, and that would be the end of it. Instead, we got a live, planetary-scale laboratory where processes are unfolding that could rewrite our understanding of astrobiology, planetology, and even the origin of life in the universe. Pressure on space agencies was growing. Groups of scientists from all over the world signed petitions demanding that Martian missions be expedited. Options were proposed for small probes that could be quickly prepared and sent to the Red Planet, with the sole purpose of investigating the anomaly zone. Such an approach does not guarantee success. Fast missions often fail due to insufficient design, but the price of delay turned out to be even higher. Every day, the processes on Mars continued, and we could miss the critical moment when the changes would be most apparent and informative. New data from Martian orbital stations showed the expansion of the temperature anomaly. It now covered an area approximately 40 kilometers in diameter, twice as large as a week ago. The growth was not explosive, but the steady trend was alarming. If the process continues at the same pace, the anomalous zone could become large enough in a few months to influence the planet's regional climate. Warm air will rise, creating local circulation, possibly lifting dust, and changing the distribution of water vapor in the atmosphere. Mars may gain its first living weather phenomenon in billions of years. Not just a dust storm born of wind, but a thermal anomaly capable of generating its own atmospheric currents. Modeling showed an interesting result. If the temperature anomaly continues to grow and becomes powerful enough, it could initiate a positive feedback loop. Warm air will rise, lowering the surface pressure. This will cause an influx of air from surrounding areas, bringing with it moisture, the trace amounts of water vapor present in the Martian atmosphere. In the anomaly zone, the temperature is higher, possibly enough for water to condense as fog or frost. This will add moisture to the local environment, which can accelerate the chemical reactions, which will release more heat, which will strengthen the upward currents. The cycle will close. On Earth, similar processes lead to the formation of weather systems, cyclones, anticyclones, and monsoons. But on Mars, the atmosphere is too thin for such global phenomena. However, locally, on the scale of tens of kilometers, such a system could exist, creating a microclimate radically different from the surrounding planet. This would be an island of relative warmth and possibly increased humidity on a cold and dry planet. And if something capable of utilizing these conditions is present in the soil of this zone, microorganisms, chemical catalysts, anything, the process could sustain itself indefinitely. The idea that Mars could come to life locally sounded fantastic, but mathematics and physics did not rule out this possibility. Planets are complex systems where small changes can lead to cascade effects. Earth's history knows examples where small fluctuations in ocean chemistry or the atmosphere triggered global climate changes, leading to mass extinctions, or conversely, explosive growth in biodiversity. Mars is much simpler than Earth in terms of active processes. There is no tectonics, no oceans, no biosphere. But precisely because of this, even a small disturbance can have disproportionately large consequences. A system in equilibrium is sensitive to shock. Astrobiologists began discussing a scenario previously considered pure science fiction. What if the 3I Atlas cloud did not just bring organic molecules, but initiated a process of terraforming in miniature? Not a global change of the entire planet that would require large-scale technology and hundreds of years of work, but a local oasis where conditions become less hostile to complex chemistry and, possibly, to life. Nature itself is demonstrating to us that planets are not static, that they can change under the influence of external factors, that space is not as isolated as we thought. This idea caused a turbulent reaction. Skeptics pointed out that we know too little to draw such conclusions. Enthusiasts spoke of the possibility of observing the birth of a new ecosystem, even if primitive and confined to a tiny area, but an ecosystem that did not originate on Earth. Philosophers discussed ethical issues. Do we have the right to intervene if the process genuinely leads to the formation of something living? Should we isolate the zone so as not to introduce Earth microorganisms that could disrupt natural development? Or, conversely, should we actively study what is happening, even if it means a risk of contamination? The discussion moved beyond science. Lawyers began studying international space treaties, trying to understand what legal mechanisms apply to a situation where changes of an uncertain nature are occurring on a planet that is legally the common heritage of humanity. Politicians debated whether a special international commission should be created to coordinate research. Religious figures questioned the theological implications. If life can arise or spread between star systems naturally, how does this relate to various pictures of the world? But amidst all these discussions, the main work continued: data collection and analysis. Martian orbital stations operated in enhanced mode, transmitting terabytes of information every day. Ground-based telescopes monitored the planet in different spectral ranges. Every image, every spectrum, every measurement added details to the picture of what was happening on the red planet. And the picture slowly became clearer, although the overall understanding remained elusive. One of the most interesting results came from radar analysis of the anomaly zone. Radar is capable of penetrating the surface for several meters, showing the structure of the subsurface layer. The data showed changes in the dielectric permittivity of the soil, a parameter that depends on the content of water, ice, and other substances. It seems that at a depth of 1 to 3 meters below the surface, processes are occurring that are changing the composition or structure of the regolith. This could be water migration, the melting of subsurface ice, and its movement under the effect of a temperature gradient. It could be the chemical transformation of minerals, or something else that we cannot yet identify. The hypothesis of a subsurface reactor emerged. If particles from the cloud penetrated the soil to a shallow depth and began interacting with minerals there, releasing heat and reaction products, the process could be more intense beneath the surface than on it. The surface of Mars is subjected to diurnal temperature fluctuations, ultraviolet radiation, and wind erosion. All this can interrupt or slow down reactions. Below the surface, conditions are more stable. The temperature changes more slowly. There is no direct sunlight and no wind. If an exothermic process is initiated there, it can proceed more uniformly and for a longer duration, creating a stable heat source that we are observing. The idea arose to conduct seismic monitoring, a station measuring Marsquakes, the remnants of the planet's seismic activity, operates on Mars. If active processes, gas release, fluid movement, chemical reactions are indeed occurring in the anomaly zone, this could create microtremors, barely noticeable vibrations that the seismometer is capable of picking up. The data began to be analyzed, and the results were unexpected. Weak but regular signals were observed in the direction of Utopia Planitia, not Marsquakes in the classical sense, but something like a hum, low-frequency oscillations that repeated with a certain periodicity. The interpretation of these signals caused a new wave of debate. Geophysicists suggested that this could be the result of thermal stresses in the soil. When material heats up and cools down, it expands and contracts, creating mechanical vibrations. But the periodicity seemed too regular for a purely physical process. On Earth, similar rhythmic signals are sometimes associated with the movement of fluids in porous rocks. Water or gas passes through cracks, creating pressure pulsations. If something similar is happening on Mars, subsurface gas, or melted ice, moving through a network of pores and cracks, this would explain the observed seismic data. But there was also a third interpretation that people were afraid to voice. Periodic oscillations are characteristic of systems with feedback, chemical oscillators, biological rhythms, and any processes where the product of a reaction affects the rate of the reaction itself, creating a cycle of activity and rest. On Earth, such rhythms are ubiquitous, from the heartbeat to the predator-prey cycles in ecology. If something similar, a self-sustaining process with internal regulation, is indeed occurring in the Martian anomaly zone, it would be a sign of complexity usually associated with living systems, or at least with pre-biological chemistry. The scientific method requires verifiable hypotheses and reproducible results, but in this case, we have no opportunity to conduct an experiment. We cannot descend to Mars, take a sample from the anomaly's epicenter, analyze it in a laboratory, and repeat the process under controlled conditions. All we can do is observe from afar, build models, compare with what we know from Earth's experience, and hope that nature gives us enough clues to solve the mystery. The month after the 3I Atlas cloud passed was coming to an end. Mars continued to change, slowly, almost imperceptibly, on a daily scale, but steadily when looking at graphs covering weeks. The temperature anomaly grew. The concentration of organic matter in the atmosphere fluctuated, but the overall trend was upward. The spectral characteristics of the surface in several regions continued to change. The seismic signals became slightly clearer. Each of these factors individually could have a trivial explanation, but their combination, their correlation in time and space, and their connection to the passage of the interstellar object, all indicated that we were observing the beginning of something significant. Humanity found itself facing a phenomenon for which we were neither technically nor psychologically prepared. We were accustomed to thinking of space as a void, of planets as dead rocks, and of life as a rare exception tied to special conditions. 3I Atlas challenged all these assumptions. Space turned out to be filled with matter that travels between stars. Planets are not isolated. They exchange substance, albeit on timescales inaccessible to human perception. And life, if it is indeed present in what we are observing, may be much more resilient and widespread than we thought, capable of surviving in interstellar space, being transported over vast distances, and awakening on new planets when conditions become suitable. Scientists continued their work, knowing that answers would not come quickly. Mars is not in a hurry to reveal its secrets. Processes there proceed at their own pace, determined by physics and chemistry, not by our impatience. But every new day of observation brought us closer to understanding. Somewhere in the data stream, in the correlations between temperature, chemistry, and seismics, in the patterns yet to be discovered, lay the key to what is truly happening on the red planet. And perhaps that key will open the door not only to the mysteries of Mars, but also to the understanding of how life in the universe is structured, how it arises, spreads, and adapts to new worlds. Mars ceased to be merely an object of study. It became a mirror in which we tried to glimpse our place in space, our own. When the temperature anomaly on Mars reached a critical point, something happened that no model had predicted. An orbital spectrometer recorded a sharp spike in radiation in a narrow range of the infrared spectrum. The wavelength corresponded to a temperature of about 15 degrees Celsius. On a planet where the average temperature hovers around -60 degrees Celsius, a spot appeared where conditions approached Earth's spring readings. This was not an instrument error. 3 independent orbital probes confirmed the data. On Mars, for the first time in 4 billion years, a zone formed with a temperature above the freezing point of water. The scientific community paused in anticipation. If the temperature had indeed risen above zero, it meant the possibility of liquid water existing on the surface, a phenomenon considered impossible in modern Martian conditions. The atmospheric pressure is too low, about 6 millibars, which is 150 times less than Earth's. At such a pressure, water cannot remain in a liquid state for long. It either freezes or immediately evaporates, transitioning from a solid phase to a gaseous one, bypassing the liquid phase. But there is an exception. If salts or other substances that lower the freezing point and raise the boiling point are dissolved in the water, the liquid can exist in a narrow range of conditions. Martian soil is rich in perchlorates, salts of perchloric acid, which actively absorb moisture from the atmosphere and lower the freezing point of water to -70 degrees Celsius. If subsurface ice in the anomaly zone began to melt due to the heat released by chemical reactions, and this meltwater mixed with perchlorates, a cryogenic brine liquid could form a solution capable of remaining liquid even in Martian conditions. Such brines have been detected on Mars before. Seasonal dark streaks on slopes that appear in summer and disappear in winter are presumably related to the movement of such liquids, but those were local, short-lived phenomena. Now we could be observing the formation of a stable source of liquid that had existed for several weeks. High-resolution cameras began daily imaging of the anomaly zone. The images showed changes on the surface, the appearance of dark spots that slowly expanded, as if something was soaking the soil from within. The structure of these spots was heterogeneous. The central area looked almost black. At the edges, the color transitioned to dark brown, and further out, it blended with the typical reddish hue of the Martian regolith. Spectral analysis showed a change in reflectivity. The surface began to absorb more light in certain ranges, which could indicate the presence of moisture or organic compounds. A team of planetologists proposed the hypothesis of the formation of a Martian analog of Earth's hydrothermal systems. On Earth, such systems arise where groundwater is heated by magma or chemical reactions, rises to the surface, dissolves minerals, and transfers heat and substance. Unique ecosystems form around the outlets of hydrothermal vents. Bacteria and archaea use the chemical energy of dissolved compounds for metabolism, creating biomass in conditions where sunlight plays no role. These organisms, chemoautotrophs, can exist in complete darkness, in acidic or alkaline environments, at temperatures above 100 degrees Celsius or close to zero. If such a system is indeed forming on Mars, even a primitive one, even a cold one by Earth standards, it creates a niche where life could exist. Not necessarily Earth life carried by meteorites or accidental contamination from space probes. Perhaps indigenous Martian life that has been dormant for billions of years in deep subsurface layers, in pockets of ice and brine, protected from radiation and the extreme surface temperatures, or life brought by the 3I Atlas cloud spores, structures capable of anabiosis, or molecular machines that retain the ability to replicate after millions of years of travel through the interstellar void. The debate over the nature of the processes reached a peak. Every new data publication caused an avalanche of comments, preprints, and alternative interpretations. The conservative wing insisted on a purely geochemical explanation. The interaction of interstellar material with Martian minerals initiated exothermic reactions that continue due to the chemical energy accumulated in the soil over billions of years. The radicals spoke of biological activity, pointing to patterns in the data that resembled metabolic rhythms. Between these extremes was a spectrum of opinions, from cautious suggestions of pre-biological chemistry to bold statements about observing panspermia in action. One of the leading astrobiologists published a provocative article proposing criteria for distinguishing living and non-living systems in the context of Martian observations. The traditional definition of life includes the ability for metabolism, growth, reproduction, and evolution. But on other planets, life may take forms that do not fit these categories. Perhaps there are boundary states, systems that exhibit some signs of life but not all. Crystals grow and reproduce their structure but do not metabolize. Viruses reproduce and evolve but require a host. Prions transmit information through changes in protein shape without having a genome. Where does the boundary between chemistry and biology lie? In the case of Mars, the question was complicated by the fact that we could not conduct direct tests. On Earth, numerous methods are used to determine the presence of life: microscopy, culturing, genetic analysis, and the search for specific biomolecules. On Mars, we only have remote observations, spectra, temperatures, seismic signals, and images. This is enough to detect anomalies, but insufficient for definitive conclusions. We see the symptoms, but cannot make a diagnosis. Parallel to this, a second line of research developed: the study of 3I Atlas itself. The object approached perihelion and began exhibiting signs of activity that surpassed all expectations. Its brightness increased tensfold. Its tail stretched for millions of kilometers. The emission spectrum became incredibly rich. Lines of dozens of different molecules were detected, from simple diatomic ones to complex organic structures. This was not just ice vaporizing under the influence of solar heat. It was an entire chemical factory, releasing the products of millions of years of interstellar evolution. Analysis showed the presence of molecules that are associated with biology on Earth: amino acids, nitrogenous bases, and lipid-like compounds. But the isotopic composition differed from Earth's. The ratio of carbon-12 to carbon-13 was different. Nitrogen had an unusual isotope distribution. Hydrogen showed enrichment in deuterium, a heavy isotope characteristic of cold interstellar clouds. These differences served as a chemical signature, proving that the material genuinely formed outside the solar system in conditions where other sources of elements dominated. Of particular interest was the discovery of chirality in some organic molecules. Chirality is the property of a molecule to exist in two mirror image forms that cannot be superimposed by rotation, like the left and right hands. Many biologically important molecules are chiral: amino acids, sugars, and certain lipids. On Earth, life uses almost exclusively left-handed amino acids and right-handed sugars. This is called homochirality, and its origin remains one of the mysteries of biochemistry. Why did nature choose exactly this combination, and not the opposite or a mixture? Analysis of the material in the 3I Atlas tail showed that amino acids there also exhibited a predominance of one of the chiral forms, but not the one that dominates on Earth. If Earth organisms prefer L-amino acids, an excess of D forms was observed in the interstellar material. This could be the result of purely physical processes. Polarized radiation from young stars is capable of selectively destroying one of the chiral forms, creating asymmetry. But it could also indicate that the material passed through biological processes in its native system, where life evolved with a different chiral choice. The idea that we are analyzing the remnants of an alien biosphere seemed fantastic, but the data did not allow it to be easily dismissed. The concentration of organic matter in the cloud was too high for purely abiotic synthesis. The molecular diversity exceeded what is observed in meteorites or comets from the Oort cloud. The presence of chiral asymmetry added another point to the list of anomalies. Each factor individually had alternative explanations, but their combination forced one to consider: Are we observing cosmic-scale archaeology, the remains of a world that existed millions of years ago around another star and was destroyed by some catastrophe? The concept of a necrosphere, a dead biosphere, whose remains travel through space, was developed in the works of several theorists. If a planet with a developed biosphere is subjected to destruction, a collision with a large asteroid, the explosion of a nearby supernova, or the loss of atmosphere due to stellar activity, organic material can be ejected into space. Spores, frozen cells, or fragments of biomolecules enclosed in mineral matrices, capable of protecting them from radiation. These particles become interstellar interlopers, carrying information about long-vanished life. When they reach another planet, this information can be read in the form of chemical traces, chiral asymmetry, or perhaps even fragments of genetic material. If this hypothesis is correct, Mars has now received a message from the past of another world, not in the form of a radio signal or an artifact, but in the form of molecular archaeology, chemistry that holds the memory of processes that occurred light years away and millions of years ago. The deciphering of this message could tell us what life on that planet looked like, what metabolic pathways it used, and in what environment it existed. This would be the first contact, not with a living civilization, but with its chemical heritage, a more subtle but no less significant moment in human history. Meanwhile, the processes on Mars continue to evolve. The dark spots on the surface expanded, and their structure became more complex. Radial patterns appeared, as if something was spreading from the center to the periphery, following cracks or pores in the soil. Spectral analysis showed that the chemical composition of these patterns differed depending on the distance from the center. In the very center, complex organic compounds and signs of high humidity dominated. At the periphery, inorganic salts and oxides predominated, and organic matter was present in trace amounts. This resembled the zoning observed in Earth's hydrothermal systems, where different chemical conditions create a gradient, and different types of microorganisms thrive at each step of this gradient. Mathematical modeling showed that the observed patterns could arise in systems with diffusion and reaction, a class of processes described by reaction-diffusion equations. These equations are applied to model a wide range of phenomena, from the spread of epidemics to the patterns on animal skins, from the formation of sand dunes to the growth of bacterial colonies. The key point is the presence of a local source of substance or energy that spreads in space and simultaneously undergoes transformation. If such a mechanism is indeed operating on Mars, it indicates self-organization, the ability of a system to create ordered structures without external control. Self-organization is a fundamental property of complex systems, from crystals to living organisms. Water molecules self-organize into a snowflake with hexagonal symmetry. Sand grains self-organize into dunes under the action of wind. Neurons self-organize into a brain capable of thought. Somewhere between the simple physical self-organization of crystals and the complex biological self-organization of living beings lies a boundary that we are attempting to pinpoint. Martian patterns may be located precisely in this border zone, too complex for pure physics, yet not unambiguous enough to confirm biology. A group of scientists from the University of Tokyo applied machine learning methods to analyze the temporal dynamics of the patterns. They trained a neural network to recognize different types of processes: geological, chemical, biological, based on how the spatial structures change over time. They then fed the system a sequence of images of the Martian anomalous zone, taken over several weeks. The result proved unexpected. The algorithm classified the two processes as having characteristics intermediate between chemical self-organization and the growth of bacterial colonies. The model's confidence was low, approximately 60%, which indicated the uniqueness of the observed phenomenon, lacking exact analogues in the training dataset. Critics noted that machine learning does not provide an understanding of the mechanisms. It merely finds statistical regularities in the data. The neural network cannot explain why the patterns resemble biological ones. It simply detects similarity in the mathematical feature space. But proponents of the method emphasized that statistics often point the way to new discoveries. If an algorithm trained on terrestrial processes sees a similarity between the Martian patterns and biological systems, perhaps there are deep mathematical principles unifying these phenomena, universal laws of self-organization that operate independently of specific chemistry or planet. Seismic monitoring continued to record periodic signals from the anomaly zone. The oscillation frequency was approximately 1 cycle per Martian day, which is 2,437 minutes. This could be related to diurnal temperature fluctuations. During the day, the surface heats up, triggering more active reactions. At night, it cools down, and the process is slow. But a detailed analysis showed that the phase of oscillation does not coincide with local noon or midnight. Peak activity occurred in the morning hours and the minimum in the evening. Such a shift could indicate that the process is reacting not to the current temperature, but to its rate of change, or that there is a time delay. The thermal inertia of the regolith creates a lag between solar heating and the maximum activity of the reactions. An alternative interpretation suggested that the rhythm is determined not by external factors, but by the system's internal dynamics. On Earth, many biological processes exhibit circadian rhythms, daily cycles of activity that persist even under constant illumination because they are controlled by internal biochemical oscillators. If the Martian system contains elements capable of such autonomous rhythmicity, it would be a strong argument in favor of its biological or pre-biological nature. Non-living chemical systems rarely exhibit stable oscillations, not tied to external periodic influences. The debate shifted to defining the criteria for life. The classical definition, based on metabolism and reproduction, was developed for terrestrial organisms and may not be suitable for alien biology. Some researchers proposed more abstract criteria: the ability of a system to maintain itself far from thermodynamic equilibrium, utilizing external energy flows. By this definition, life is a dissipative structure that exists as long as a flow of energy or matter passes through it. A candle flame fits this criterion, but is not considered alive. Where should the line be drawn? Philosophers of science noted that the problem of defining life reflects a deeper question. Is life a qualitatively distinct phenomenon, or merely a highly complex form of chemistry? On Earth, the transition from non-living to living matter occurred continuously, through stages of increasing complexity from simple organic molecules to self-replicating systems, from the RNA world to cells with DNA and proteins. There is no sharp point where one can say, life began here. Perhaps life is a continuum, not a dichotomy, and the Martian processes are located somewhere in the middle of this continuum, demonstrating some, but not all, signs of living systems. This discussion had practical significance for data interpretation. If we demand that Martian processes fully match the terrestrial definition of life, we may miss something important: forms of matter organization not found on Earth, but which may be widespread in the universe. If we are too liberal with the criteria, we risk mistaking simple physicochemical phenomena for life, losing the specificity of biology. The balance between these extremes is an art, not an exact science. and different researchers found it at different points along the spectrum of opinions. Meanwhile, public interest in the Martian anomaly grew exponentially. News agencies transmitted updates daily. Popular science channels released videos with explanations and speculations. Social networks were abuzz with discussions, ranging from serious attempts to understand the data to conspiracy theories about information suppression. Space agencies faced unprecedented pressure. The public demanded more data, more missions, more transparency. Science, normally slow and cautious, found itself in a situation where speed mattered, and every statement was analyzed by millions of people. This created a dilemma. On one hand, openness and public engagement are important for supporting space exploration. On the other, premature statements could create false expectations or panic. What if the processes on Mars turn out to be trivial chemical reactions, and the fuss created the impression of a great discovery? What if, conversely, we are truly observing something extraordinary, but the fear of appearing sensational leads scientists to downplay the significance of the findings? Navigating these risks required not only scientific competence, but also communication skills, which not all researchers possessed. Several leading scientific organizations issued a joint statement attempting to summarize the current understanding of the situation. The document acknowledged the presence of unusual processes on Mars caused by the passage of Comet 3I Atlas and confirmed the detection of complex organics, temperature anomalies, and changes in surface patterns, but emphasized that a definitive interpretation of this data is not yet possible. Additional observations are required, preferably direct analysis of samples from the site. Until then, any conclusions remain preliminary, and the scientific community urged caution in claims about life on Mars or other extraordinary assertions. The statement was met with a mixed reaction. Part of the public perceived it as an attempt to suppress the topic. Conspiracy theorists saw it as evidence of a truth cover-up, but most scientists supported the cautious tone, understanding that the reputation of science depends on the ability to distinguish verifiable facts from interpretations. History had seen examples where hasty announcements about the discovery of life on Mars turned out to be erroneous. From the controversies surrounding the Allen Hills 84001 meteorite, where structures resembling fossilized bacteria turned out to be minerals, to the Viking experiments, whose results still lack unambiguous interpretation. Against the backdrop of scientific debates and public discussions, the processes on Mars continued according to their own laws, indifferent to human interpretations. The dark surface patterns reached a size of approximately 80 kilometers in diameter. The thermal anomaly stabilized. Heat dissipation into the environment balanced the heat generation, creating a steady state. The concentration of organics in the local atmosphere plateaued, fluctuating within a narrow range. The system found its equilibrium, a dynamic one, maintained by a constant flow of energy from chemical reactions, but stable in its macroscopic characteristics. This stationary state was interesting in itself. In thermodynamics, equilibrium means maximum entropy, complete randomness, the absence of structure. But the Martian system demonstrated orderliness, patterns, gradients, periodicity. Such states are called dissipative structures, or non-equilibrium stationary states. They exist far from thermodynamic equilibrium, maintaining low local entropy at the expense of increasing the entropy of the surroundings. Classic examples include hurricanes, Baynard convection cells, and chemical oscillatory reactions. Life is the most complex example of such structures, capable of self-replication and evolution. The emergence of a dissipative structure on Mars following the introduction of interstellar material can be viewed as an experiment in the self-organization of matter under unusual conditions. If we consider the universe as a space of possibilities for the formation of complex systems, different planets represent different points in that space. They have different combinations of temperature, pressure, chemical composition, and energy sources. Most combinations lead to simple, unorganized states, but some fall into regimes where self-organization is possible. Earth is clearly in such a regime. Here, self-organization reached its peak in the form of the biosphere. Mars was on the brink. The conditions were almost suitable, but something was missing. Comet 3, I-Atlas, might have introduced the missing component, shifting the system into the parameter space where self-organization becomes possible. If this hypothesis is correct, we are observing the birth of complexity from simplicity, a process that underlies all evolution in the universe, from the Big Bang to modern galaxies, stars, planets, and life. In the first moments after the Big Bang, matter was nearly homogeneous. Only tiny quantum fluctuations disrupted the perfect smoothness. But these fluctuations were amplified by gravity, transforming into structures. First, gas clouds, then stars and galaxies. In stars, hydrogen was fused into helium, then into carbon, oxygen, and iron. Chemical diversity emerged. Supernova explosions scattered these elements, enriching the interstellar medium. New stars formed from the enriched gas, with planets where the chemistry became even more complex. On some planets, life appeared, adding another level of organization. Mars may fit into this picture as a place where the next step of self-organization is happening under our observation, not on the scale of billions of years and light years, but here and now, on a planet we can study with unprecedented detail. This is a window into the universal processes that shape the cosmos, making it not cold and dead, but capable of giving birth to ever more complex forms of matter organization. Understanding these processes is key to answering fundamental questions. How widespread is life in the universe? How does it arise? What conditions are necessary? Are there universal laws of biology that work independently of specific chemistry? As October drew to a close, the Martian anomaly remained the focus of the astronomical community. New observations were planned using the most powerful telescopes. The possibility of fast missions was discussed, small probes that could be sent to the Red Planet in the coming months. But everyone understood that even the fastest mission would reach Mars no sooner than a year after launch, and then months would be needed for descent, finding a suitable landing spot, and beginning operations. The processes on the planet could significantly change during that time. They might transition into a new phase, stabilize completely, or even die down if the chemical energy fueling them is exhausted. Time was working against us, but also for us. Each day provided new data, allowing us to test hypotheses and filter out incorrect models. Slowly, step by step, the picture became clearer. We still didn't know definitively what was happening on Mars. Was it life, pre-biology, exotic chemistry, or something we don't yet have a name for? But we knew we were observing something unique, a moment when a planet changes under the influence of interstellar matter, when the boundaries of the possible expand, when the cosmos shows us that it is full of surprises, and our understanding of the universe is still incomplete. Mars was silent, but its silence was more eloquent than any words. It spoke of secrets yet to be revealed, of mysteries awaiting their solutions in the red dust of the ancient planet. Everything changed on the 23rd day after the thermal anomaly stabilized. A Chinese orbital spacecraft, conducting routine infrared scanning of the surface, detected a second point of elevated temperature, approximately 400 kilometers from the first, in the region of the ancient Valles Marineris, the largest canyon system in the solar system. Initially, this was considered a reflected signal or a technical error, but subsequent measurements confirmed it. A second center of activity had appeared on Mars, exhibiting the same characteristics as the zone in the Utopia Planitia. The appearance of a second center changed the entire picture. If the anomaly had been singular, it could have been explained by a chance coincidence of factors, a favorable combination of regolith composition, interstellar particle concentration, and local geology. But two independent zones, separated by hundreds of kilometers, pointed to a systemic process. Something in the composition of Comet 3I, Atlas, was triggering reactions wherever it encountered suitable conditions. And these conditions, judging by the locations of the centers, were linked to ancient water structures. One was in a former oceanic basin, the other in a canyon system where rivers flowed and lakes formed billions of years ago. Analysis of geological maps revealed a worrying pattern. Both zones were located in regions with a high content of phyllosilicates, clay minerals that form in the presence of water and can preserve organic molecules for billions of years. On Earth, such minerals play a key role in chemical evolution. They serve as catalysts for the synthesis of complex organic compounds, protect molecules from degradation, and concentrate reactants in their micropores. Some theories on the origin of life suggest that the first self-replicating molecules arose precisely on the surface of clay particles, where conditions for complex chemistry were created. If the Martian phyllosilicates are indeed acting as catalysts for the processes initiated by the interstellar material, this would explain the selectivity of the anomalies. Not the entire planetary surface reacted to the cloud, only those areas where ancient water left a mineralogical legacy capable of sustaining complex chemistry. This transformed Mars into a mosaic of potential centers of activity, where dormant chemical complexity could be awakened by the right stimulus. Comet 3I Atlas proved to be that stimulus, and now the planet was demonstrating that its dead appearance is deceptive. Beneath the red dust, the potential for change was preserved. A few days later, a third and fourth anomaly were discovered in Gale Crater, where the Curiosity rover was operating, and in the Tharsis volcanic plateau region. Each new center followed the same pattern. An ancient water region, phyllosilicates in the soil, a gradual temperature increase, the appearance of organic signatures in the atmosphere, and the formation of dark patterns on the surface. The process ceased to be a local phenomenon. It was taking on a planetary scale, though it remained geographically confined to specific geological conditions. Mathematical modeling showed that if the trend continues, Mars could have between 15 and 20 active zones within a few months, each tens of kilometers in size. The total area would be less than 1% of the planet's surface, but the impact on the atmosphere could be disproportionately large. Organic molecules emitted from these zones would be spread by winds, changing the chemical balance of the entire atmosphere. Water vapor rising from local heat sources could create cloud cover, a phenomenon extremely rare on modern Mars, where the atmosphere contains almost no moisture. The most intriguing finding was that the centers did not exist in isolation. Spectral analysis of the atmosphere showed an increased concentration of certain molecules in the air between the active zones. It was as if they were exchanging chemical signals. On Earth, similar phenomena are observed in ecosystems. Plants release volatile compounds that affect the growth and metabolism of other plants at a distance. Trees in a forest are connected by a network of chemical communication, coordinates their defense against pests, resource distribution, and even diurnal rhythms. The idea that the Martian anomalies might be exhibiting similar coordination sounded fantastic, but the data did not allow it to be easily dismissed. A group of biochemists proposed the hypothesis of quasi-organismic self-organization. According to this idea, the individual centers are not living organisms in the traditional sense, but together they form a distributed system that exhibits properties similar to life: information exchange, coordinated behavior, perhaps even primitive adaptation to environmental conditions. An analogy is the slime mold colony on Earth, where thousands of single-celled organisms unite into a single structure capable of complex behavior unavailable to individual cells, or colonies of social insects, where each individual is simple, but together they create a superorganism with emergent properties. Critics pointed out that such coordination requires a mechanism for information transfer. On Earth, this is chemical signals, pheromones, electrical impulses. On Mars, the distances between centers are measured in hundreds of kilometers. The atmosphere is thin, and the winds are unpredictable. How can molecules reliably transmit information in such conditions? One idea is the use of atmospheric currents as a transmission medium. The Martian atmosphere, though thin, has a global circulation with predictable patterns. If the centers release specific molecules at certain times, these molecules will be carried by the wind along known routes, reaching other zones after a few days or weeks. This is slow communication, but on geological timescales, even weeks are a fleeting moment. An even more radical hypothesis emerged: that we are not observing the spontaneous emergence of new processes, but the awakening of something ancient. If life existed on young Mars, and the conditions 4 billion years ago were suitable, it might have adapted to the gradual deterioration of the climate, retreating deeper under the surface, slowing its metabolism to a near stop, transforming into spores or other resistant forms, capable of surviving billions of years of unfavorable conditions. Terrestrial microorganisms demonstrate incredible tenacity. Bacteria have been extracted from amber tens of millions of years old and successfully cultured. Spores survive in space, in nuclear reactors, in acids and alkalis, at temperatures from near absolute zero to the boiling point of water. Martian life, if it existed, might have developed even more perfect survival mechanisms. Over 4 billion years of evolution on a dying planet, the selective pressure would have been extreme. Only those forms that could withstand cold, vacuum, radiation, lack of water, and nutrients would survive. Such organisms would be completely unlike terrestrial life in its active form. They would be more like cryptobiotic structures waiting for the moment when conditions improve. And Comet 3I Atlas, by bringing organics, water, perhaps critical elements or catalysts, became the signal for reawakening. The ancient Martian biosphere began to revive after billions of years of suspended animation. This hypothesis explained the selectivity of the process, why the activity was concentrated in ancient water basins. It was precisely where lakes and rivers once existed that Martian life would have been most widespread. It was there that its remnants or spores would have the highest density. When conditions changed due to the interstellar impact, the awakening began where the concentration of dormant organisms was sufficient to initiate visible processes. It also explained the coordination between the centers. If this truly is biology and not just chemistry, the organisms might be using quorum sensing strategies, known in terrestrial bacteria, where a population activates only upon reaching a critical density determined by the concentration of signaling molecules. But this hypothesis was impossible to verify without direct sample analysis. The debates over the nature of the processes reached a point where further progress required empirical data that we lacked. Remote observations provided the maximum possible information. Now, microscopes, culture, media, and genetic analysis were needed. If Martian organisms even possess something akin to DNA or RNA, the pressure on space agencies became unbearable. Petitions gathered millions of signatures. Politicians in different countries declared their readiness to fund emergency missions, but the reality of spaceflight is stubborn. You can't just launch a rover in a few weeks. Compromise options were discussed. One of them was to redirect the existing Curiosity rover, located in Gale Crater, to the nearest anomalous zone. The distance was about 30 kilometers. For the rover, this means months of travel, but it's feasible. The problem is that Curiosity was designed for other tasks. Its instruments are not optimized for the search for life. Nevertheless, it could take soil samples, perform basic chemical analysis, and take detailed images. This would be better than orbital observation. The decision to redirect was made at the highest level. The risks were weighed. The rover is old. Every kilometer of travel increases the probability of breakdown, and losing the only working apparatus near the zone of interest would be a catastrophe. Meanwhile, Comet 3I Atlas continued its journey through the inner solar system. The object passed perihelion and began to move away from the Sun, but its activity did not decrease. On the contrary, spectra showed the release of increasingly complex molecules. Astronomers suggested that the heating had penetrated deep into the object's body, reaching layers that had remained frozen since its formation. These ancient ices were now evaporating, releasing material that had never been exposed to interstellar radiation or sunlight. This was a time capsule opening right before us. Spectral lines indicated the presence of molecules that on Earth are found only in living organisms or their remains. Porphyrins, similar to chlorophyll and hemoglobin, long-chain lipids characteristic of cell membranes, possibly even fragments of nucleic acids. Although the identification of the latter was ambiguous due to the complexity of the spectra, every new observation added weight to the hypothesis that Comet 3I Atlas carried not just organics, but biological material. The remains of life that existed near another star and were destroyed by some catastrophe that scattered the fragments of that biosphere into interstellar space. The idea of a necropolis of star systems, a cemetery of worlds traveling through the galaxy as asteroids and comets gained new resonance. Perhaps the cosmos is full of such wanderers, carrying the memory of lost civilizations and biospheres. Every system where life arose and was then destroyed left behind a material legacy. Molecules, spores, perhaps even preserved artifacts encased in rock and ice. These fragments travel for millions of years, sometimes entering new systems where they can trigger a chain of events, from simple chemical enrichment to, potentially, the initiation of a new biosphere through panspermia. The philosophical significance of this idea is hard to overstate. If life in the universe is connected through material exchange between star systems, then every biosphere is not an isolated phenomenon, but a node in a galactic network of biological information. Terrestrial life may contain the molecular echo of dozens of other worlds, elements that reach the young Earth via meteorites and comets, some of which might have been interstellar travelers. We may be descendants not only of terrestrial chemistry, but also of chemistry that arose near distant stars, traveled light years, and finally found a new home on our planet. This concept blurred the lines between the native and the alien. If life spreads between stars naturally, then any encounter with extraterrestrial biology may turn out to be a meeting with distant relatives whose molecular ancestors once shared a common origin with ours. The tree of life may have roots that extend not to one primary organism on one planet, but to a distributed network of chemical evolution, spanning multiple worlds and stretching back billions of years into the past. perhaps even to the epoch when the universe was young and the first-generation stars were just beginning to synthesize heavy elements. On Earth, meanwhile, debates about biosafety raged. If life was indeed activated or introduced on Mars, what risks does this pose for future missions? The planetary protection protocols developed by space agencies assumed the sterilization of all spacecraft sent to planets where life is possible to avoid contamination. But these protocols were created on the assumption that Martian life, if it exists, would be weak, vulnerable, and in need of protection from aggressive terrestrial microorganisms. Now the situation could be different. If the Martian processes are truly biological and exhibit resistance to extreme conditions, the encounter of two biospheres could have unpredictable consequences. Terrestrial microorganisms brought to Mars by spacecraft might compete with local forms for resources: water, organics, minerals. Horizontal gene transfer is possible if both life forms use compatible genetic mechanisms. Symbiotic or parasitic relationships are possible. On Earth, history knows many examples where the introduction of species into new ecosystems led to catastrophic consequences: the extinction of native species, the disruption of food chains, and cascade changes in ecology. Mars is much simpler than Earth in the biological sense. If life exists there, it is likely microbial communities without complex ecological interconnections. The introduction of terrestrial biology could completely transform such a system. The reverse risk: the possibility that Martian organisms brought to Earth with samples could be dangerous to the terrestrial biosphere, had been discussed since the first missions. Protocols suggest that samples from Mars be placed in Mars maximum containment laboratories, similar to those used for handling the most dangerous terrestrial pathogens. But how sufficient are these measures against organisms that evolved in completely different conditions and may have unpredictable properties? Martian microbes, adapted to extreme conditions, might be impervious to terrestrial antibiotics, have a metabolism based on different chemical pathways, and release compounds toxic to terrestrial life. The probability of a catastrophic scenario was rated as low by most experts. The differences between the environments are too great, and the adaptation of microorganisms to their native conditions is too specific. Terrestrial bacteria, perfectly adapted to life in the human gut, die in ocean water. Martian organisms, if they exist, are adapted to cold, dryness, and low-pressure conditions found on Earth, only in places like the Antarctic highlands. But low probability does not mean impossible. And when the stake is the biosphere of an entire planet, even small risks demand serious consideration. Legal aspects also sparked controversy. The Outer Space Treaty, signed during the Cold War, declares celestial bodies the common heritage of mankind and prohibits their national appropriation. But who has the right to decide what to do with Martian life if it is confirmed? Should we preserve the planet in its pristine state, creating a biological reserve of cosmic scale? Or do we have the right to study, modify, and perhaps use these organisms for scientific and practical purposes? Do we have moral obligations to the hypothetical Martian biosphere, even if it consists only of microbes? These questions went beyond science, touching upon ethics, philosophy, and even theology. Various religious traditions answered the question of humanity's place in the universe and its responsibility to other life forms differently. Some saw the potential discovery of Martian life as proof of the universality of creation. Others saw it as a challenge to anthropocentric notions of humanity as the pinnacle of creation. Philosophers debated whether the discovery of extraterrestrial life expands the moral circle, the circle of beings to whom ethical obligations apply, or whether microbes remain outside it, regardless of their planet of origin. Amidst these high debates, The Martian processes continued to develop according to their own logic. The number of active zones grew to 8. Their cumulative area reached several thousand square kilometers. The planet's atmosphere began to show changes noticeable, even on a global scale. The concentration of methane increased by an order of magnitude compared to the background level. Water vapor showed local spikes over the planned, anomalous zones. Traces of molecules that could be products of biological metabolism appeared. Hydrogen sulfide, ammonia, and simple organic acids. Climate models showed that if the process continues, the Martian atmosphere could change so much within a few years that it would affect global temperatures. The greenhouse effect from the additional methane and water vapor is small. The atmosphere is too thin. But even a rise in the average temperature by a few degrees could trigger positive feedback loops. More heat means more sublimation of the polar caps, which consist of carbon dioxide and water ice. More carbon dioxide and water in the atmosphere mean a stronger greenhouse effect. A stronger greenhouse effect means more heat. The cycle could be self-reinforcing, albeit slow. The Martian climate is inert. Changes there are measured in decades and centuries, not years, but the fact remained. For the first time in billions of years, Mars was showing signs of climate change caused not by astronomical factors like orbital changes or solar activity, but by processes on the planet itself. This was similar to how, on Earth, the activity of living organisms, first photosynthetic bacteria, then plants, transformed the atmosphere, filling it with oxygen and creating conditions for complex life. The Martian changes were orders of magnitude weaker. It was not about terraforming in the full sense of the word, but the trend was the same. Life, if it truly is life, was changing the planet. Scientists began to use the term marsoforming, the adaptation of the planet to the needs of the supposed Martian organisms. If the hypothesis about the awakening of the ancient biosphere is correct, these organisms were not just reacting to the changed conditions, they were actively creating an environment more favorable for their metabolism and reproduction. By releasing greenhouse gases, they increased the temperature. By producing water vapor, they increased humidity. They might also have synthesized compounds that protected them from ultraviolet radiation or improved nutrient availability. This was ecological engineering, on a planetary scale, carried out by creatures the size of microns. On Earth, similar processes are called biogenic environmental change. Microorganisms in the soil change the $X pH, mineral concentration, and soil structure, creating conditions for plant growth. Plants release oxygen, change the surface albedo, and influence the water cycle. Animals process organics, transport nutrients, and alter landscapes. The entire Earth biosphere is a self-sustaining system where life creates and maintains the conditions for its own existence. Mars was perhaps demonstrating the initial stage of such a process, not developed biosphere, but its embryo. The first steps of self-organization which, with favorable development, could lead to something greater. But how long would this take? Mathematical models gave a range from thousands to millions of years, depending on assumptions about the speed of the processes and the availability of resources. Mars is energy poor. The Sun provides less than half of what Earth receives. Geothermal activity is virtually zero. Mars is poor in available water. Most of it is frozen in the polar caps and subsurface ice. Mars was poor in organics before the arrival of 3I Atlas. Its concentration was negligible. In such conditions, a biosphere, even if it begins to develop, will grow very slowly, perhaps never reaching a complexity comparable to Earth's, but it could reach a level sufficient for Mars to cease being a dead planet. Microbial mats covering patches of soil. Chemosynthetic communities around sources of subsurface heat. Perhaps primitive multicellular forms, after millions of years of evolution. Not flowering gardens and forests. The Martian biosphere will always be sparse by terrestrial standards, but a living planet in the minimalist sense, a place where evolution continues to write its story, creating forms adapted to extreme conditions. And humanity found itself a witness to the beginning of this story. We saw the moment when the dead becomes the living, when chemistry crosses the invisible boundary and turns into biology. This was a process that happened on Earth 4 billion years ago, and we will never know the details of that ancient event. It left no direct traces, only indirect evidence in isotopic anomalies and chemical signatures in the oldest rocks. But on Mars, perhaps, we were observing a repetition of this fundamental transition in real time, with a full set of modern instruments capable of recording every detail. The irony was that the more we observed, the less certain we were of the interpretation. Each new fact allowed for multiple explanations. The data was rich enough to rule out the simplest models, but not detailed enough to choose between more complex alternatives. We were stuck in epistemological uncertainty. We knew something important was happening, saw signs of processes not observed on Mars for billions of years, but could not confidently say, this is life, pre-biology, or just exotic geochemistry, triggered by a unique set of circumstances. This uncertainty was agonizing for scientists, accustomed to precision and unambiguousness, but it was also thrilling. We were at the forefront of knowledge, where the map ends and the unknown begins. There were no textbooks to provide answers, no precedents to rely on. Only data, logic, and the collective mind of researchers around the world trying to assemble a picture from fragmented pieces of information. Mars was silent, continuing its processes without regard for human interpretations. The dark patterns on its surface were expanding. The atmosphere was slowly changing. The thermal anomalies were pulsating in their diurnal rhythms. Somewhere in the red dust, in the cracks of ancient rocks, in the frozen brines beneath the surface layers, something was happening that might change this planet forever. And we watched, recorded, analyzed, trying to understand whether we were missing the greatest discovery in the history of science, or, conversely, seeing in the data what we wanted to see, projecting terrestrial concepts of life onto processes that might be of an entirely different nature. The answer was, somewhere out there, on Mars, hidden in the molecules and structures that we could not yet investigate directly. And time, the slow Martian time, was counting down the moments until the day when that answer might be obtained. The decision was made at a level usually inaccessible to scientific questions, in the halls where issues of national security and global threats are discussed. The heads of the space agencies of 5 major powers held a closed video conference lasting almost 8 hours. The details of the discussion remained classified, but the result was announced publicly. Humanity would send an emergency mission to Mars, not in decades, as interplanetary expeditions are usually planned, but in the shortest possible time. The goal, to obtain direct samples from the zone of activity and definitively answer the question that was now keeping millions of people across the planet awake. What exactly is happening on the red planet? The project was named Genesis, a symbolic name referring to the beginning, the moment of birth, of something new. Design bureaus worked around the clock, using existing developments and simplifying the design as much as possible to meet the tight deadline. The probe would be small, only 300 kilograms, but equipped with critically important instruments. A high-resolution microscope capable of distinguishing structures sized in fractions of a micron. A full-range spectrometer, a device for taking samples from a depth of up to 2 meters. a protected container for sealing the samples. Most importantly, a biodetection system developed specifically for this mission, capable of detecting signs of metabolic activity, even if it is based on chemistry different from Earth's. But even with maximum acceleration, the launch could not take place sooner than several months. The time required for assembly, testing, and preparing the launch vehicle, and the flight to Mars, would take another 7 to 8 months, depending on the trajectory and the planet's positions. This meant that we would not receive direct data from the surface until a year from now. During this time, the processes on Mars could pass through several phases of development, reach a new equilibrium, or even die down if the chemical energy fueling them is exhausted. We were doomed to observe from afar, gathering indirect evidence, while the crucial information remained unattainable. The Curiosity rover received a directive to redirect to the nearest anomalous zone. The operations team in California developed a route that minimized risks, bypassing large rocks, avoiding steep slopes, and choosing firm soil where the wheels would not get stuck in the sand. Every meter of the journey was planned with a surgeon's meticulousness. The rover cost billions of dollars and decades of work. Losing it due to carelessness would be unforgivable. The movement began, slow, cautious, but relentless. 200 meters per day, sometimes less if the terrain was difficult. The goal was approximately 30 kilometers away. This meant months of travel, but there was no alternative. While the rover crawled across the Martian surface, orbital observations continued to yield a stream of data, each portion of which reinforced the feeling that we were observing something unprecedented. The number of active zones grew to 12. Their distribution across the surface showed a pattern. They formed something like a network where the distances between neighboring centers ranged from 200 to 500 kilometers. This could be a coincidence determined by geology. It is at such distances that ancient water basins of a suitable size located, but it could also indicate an optimal distance for some type of interaction between the zones. The spatial scale at which the system worked most effectively, spectral analysis of the atmosphere between the centers, revealed an intriguing feature. The concentration of certain molecules, primarily complex organic compounds with nitrogen groups, oscillated with a period of about 10 Martian days. This was too long for atmospheric processes, which usually have periods from hours to days, but too short for seasonal changes. One interpretation was chemical clocks, an oscillatory reaction where the products regulate the speed of their own production, creating concentration cycles. Such reactions are known on Earth. A classic example is the Belousov-Zhabotinsky reaction, where the solution periodically changes color due to the oscillation of intermediate product concentrations. But the Martian oscillations were occurring in the atmosphere on a planetary scale, involving a multitude of different molecules. The synchronization of such a complex system required a coordination mechanism. Mathematical modeling showed that by assuming an exchange of signaling molecules between active zones via atmospheric transport, oscillations with the observed period could be obtained. This was similar to how fireflies in a tropical forest synchronize their flashes, creating a collective rhythm, despite each insect acting independently, reacting only to the signals of its neighbors, or how pacemaker cells in the heart coordinate the contraction of the entire organ through electrical impulses. The idea of Martian planetary synchronization seemed fantastic, but alternative explanations were even more strained. A chance coincidence of the rhythms of a dozen independent chemical processes is statistically improbable. An external rhythm driver, solar activity, magnetic storms, was checked, and there was no correlation. It remained to assume that the system indeed possessed the ability for self-organization on a planetary scale, a property that on Earth is demonstrated only by the biosphere as a whole, where the circulation of carbon, nitrogen, and oxygen is coordinated through a complex network of biological and geochemical processes. The realization of the scale of what was happening came not at once, but gradually, as data accumulated. Mars was not just demonstrating local chemical anomalies. The planet was showing signs of transforming into a system with global feedback loops, where different regions influenced each other, creating emergent behavior not reducible to the sum of local processes. This was a qualitative leap, which in Earth's history marked the moment when the first microbial communities began to influence the planetary environment, paving the way for billions of years of further evolution. The philosophical implications were mind-boggling. If a planet can spontaneously transition from a dead state to a living one with the right stimulus, in this case, interstellar material, it radically changes our estimates of the prevalence of life in the universe. Perhaps the origin of life does not require millions of years of gradual chemical evolution in ideal conditions. Perhaps it can happen quickly, almost catastrophically, when the dormant potential of a planet meets the right catalyst. Mars held this potential for 4 billion years. Ancient organics in phyllosilicates, frozen brines in the soil, minerals capable of serving as catalysts. Comet 3, I-Atlas brought the missing ingredient, and the system activated. This meant that billions of planets in the galaxy might exist in a similar dormant state, not quite dead, but not fully alive, on the brink between the two states, awaiting a trigger that will shift them into the parameter space where self-organization is possible. Interstellar objects, constantly coursing between star systems, could be such a trigger, carriers of complexity that initiate processes in worlds where local chemistry has reached a dead end. The universe turns out to be not a collection of isolated islands of life in an ocean of dead matter, but a network of interconnected systems where information in the form of molecules, structures, and chemical patterns is transmitted between worlds, creating opportunities for the emergence of complexity where it could not arise spontaneously. The scientific community was divided on what to call the observed processes. Conservatives insisted on the term abiotic self-organization, acknowledging the complexity of the system, but avoiding the assertion of biology. Radicals spoke of proto-life, or even an alternative biosphere. Between them was a spectrum of intermediate positions: pre-biological chemistry, autocatalytic networks, and dissipative structures with high complexity. The lack of consensus reflected a deep problem. Our definition of life was developed for terrestrial organisms, and when we encounter a system that possesses some, but not all, signs of life, language proves inadequate. One theorist proposed a continuum scale of aliveness instead of the dichotomy of living, non-living. At one end are simple molecules exhibiting only physical interactions. At the other are complex organisms with metabolism, reproduction, and evolution. In between are many intermediate states: autocatalytic reactions, self-assembling structures, the RNA world, primitive cells, and multicellularity. The Martian processes were located somewhere in the middle of this scale, definitely more complex than simple chemistry, but it was unclear whether they had reached the level we would recognize as biology. Perhaps it was something unique to Martian conditions, a form of matter organization not found on Earth, because evolution took a different path here. The public reaction to the unfolding situation was uneven. Most people followed the news from Mars with interest, but without panic. The processes there were too slow, too distant to cause immediate alarm. Popular science channels explained complex concepts in accessible language, helping a wide audience understand the significance of what was happening. Conspiracy theorists wove tales of hidden agents and secret missions, Religious communities discussed the theological aspects. Science fiction writers constructed future scenarios where humanity shares the solar system with a Martian biosphere. But among the scientists directly working with the data, there was a feeling difficult to put into words. It was a mixture of excitement and anxiety, curiosity and caution, certainty in the moment's significance, and an acknowledgement of their own ignorance. Every new graph, every image from orbit, every spectrum added details, but the overall picture remained elusive, as if we were trying to discern the shape of an object by seeing only its shadow. We knew that something fundamental was happening, that the boundary between the possible and the impossible had shifted, that our ideas about planets, life, and the cosmos required revision, but the exact nature of this shift remained hidden. Comet 3, Atlas, was meanwhile leaving the inner solar system, picking up speed that would eventually carry it back into interstellar space. Its brightness was falling, its tail shrinking, and its spectra becoming poorer as it moved away from the Sun and cooled. In a few years, it will cross the orbit of Neptune and enter the Oort cloud, the distant region of icy bodies at the edge of our system. In a few more decades, it will be so far away that even the most powerful telescopes will lose sight of it. The interstellar wanderer will continue its eternal journey. Perhaps in hundreds of thousands of years, it will reach the vicinity of another star, where the scenario we observed on Mars might be repeated, but the trace it left in our system will remain. Mars is changed, perhaps forever. Even if the processes die down, the organic material introduced by the cloud will remain in the soil, in the atmosphere, and in the planet's chemistry. Future explorers will find the molecular signatures of interstellar matter, studying how it distributed across the surface and how it interacted with local minerals. This will be a layer in the geological record of Mars, marking the moment when the planet received an infusion of material from another star system, an event that perhaps happened many times throughout the history of the solar system, but was recorded in real time with such detail for the first time. For humanity, this experience will also leave a mark. We learned that the cosmos is not as isolated as we thought. Star systems exchange matter, information, and possibly life. We observed how a planet can change in weeks, not billions of years, if it receives the right stimulus. We realized that life might be a more flexible concept than terrestrial examples suggested, and we recognized how much we still don't know, how many processes, phenomena, and forms of matter organization exist in the universe, awaiting discovery. The Curiosity rover continued its journey toward the anomaly zone, covering hundreds of meters each day. Its cameras recorded the surrounding landscape, endless fields of red dust, scattered rocks, and distant mountains on the horizon. The autonomous navigation software selected the route, avoiding obstacles. Operators on Earth checked the decision, correcting it when the system erred. It was a slow dance between man and machine, separated by light minutes of signal delay, but united by the common goal of reaching the place where something is happening that may change our understanding of the universe. Every day brought new data from orbit. Every week, new articles attempting to integrate the growing array of information into a coherent theory. Discussions continued. Models were refined, and hypotheses were filtered out or gained support. Science worked as it should, methodically, critically, gradually, narrowing the space of uncertainty, separating reliable facts from interpretation, acknowledging the limits of knowledge, but relentlessly expanding them. And somewhere in this process, in the flow of data and debates, graphs and formulas, a understanding gradually crystallized, not final, not indisputable, but reliable enough for most researchers to accept. Mars was demonstrating processes that lay on the boundary between chemistry and biology, perhaps in a transitional zone where one turns into the other. Were there living organisms in the strict sense? The question remained open, but the system certainly possessed some properties of living systems: self-organization, exchange of substances with the environment, maintenance far from equilibrium, and possibly even primitive adaptation. This was not the complete answer everyone was waiting for. There was no moment of revelation when everything suddenly became clear. But this was the honesty of science. It did not promise simple answers to complex questions. It offered tools for investigation, methods for testing hypotheses, and a community for the collective search for truth. And sometimes, the result was not a categorical assertion, but a more accurate understanding of complexity, an acknowledgement that reality is richer than our categories, that nature is not obliged to fit within the frameworks we have prepared for it. Now, as you read these lines, the processes on Mars are continuing. The active zones are pulsating in their rhythms. The atmosphere is slowly changing. The dark patterns on the surface are evolving. The rover is moving toward its goal, shortening the distance by a few hundred meters each day. Scientists are analyzing data, building models, and debating interpretations. Space agencies are preparing an emergency mission that, perhaps a year from now, will bring final answers or won't, opening up new, deeper, and more intriguing questions instead. But it is already clear that we have lived through a historic moment. Not first contact with a sentient civilization, nothing so dramatic, but perhaps something more fundamental: the observation of how non-living matter crosses the boundary beyond which begins complexity capable of self-maintenance and evolution. We have seen how interstellar matter can change a planet, how the cosmos is connected by networks of material exchange, and how the potential for complexity can lie dormant for billions of years, awaiting the right moment for activation. This knowledge changes the perspective. When we look at the night sky, at the thousands of visible stars and billions of invisible ones, we now know that the space between them is not empty. It is filled with wanderers, comets, asteroids, and fragments of worlds, carrying the chemical memory of their origin. Some of these wanderers contain simple molecules: water, carbon dioxide, and ammonia. Others carry organics, complex compounds that on Earth are associated with life, and perhaps some carry life itself: spores, anabiotic cells, and molecular machines capable of replication, waiting for the moment when they enter an environment where they can awaken and begin a new cycle of evolution. If so, then life in the universe may be the result not only of local emergence on every suitable planet, but also of a global process of transfer and exchange between worlds. The galaxy may be permeated by a network of biological information, where every star system receives a contribution from others and contributes to the common pool itself. Biospheres are not isolated. They are connected through space and time, through the slow journey of molecules and structures that traverse light years, carrying within them the potential for the emergence of new complexity. This picture is both beautiful and unsettling. Beautiful because it shows the universe not as a desert where rare oases of life exist in solitude, but as a garden where seeds are spread by the wind, the slow interstellar wind, where time is measured in millions of years, but the process is relentless. Unsettling because it raises questions about our place in this system and our responsibility. If we begin to actively explore and modify other worlds, we will become part of this transfer process, but no longer a blind one, guided by random gravitational perturbations, but a conscious one, managed by intellect. Do we have the right to interfere? Should we preserve Mars in its current state, whatever that may be, as a natural reserve of planetary scale? Or can we study, change, and possibly accelerate the processes that have begun there? Is there a moral difference between natural panspermia carried out by comets and artificial panspermia that we could conduct by intentionally introducing microorganisms to other planets? These questions do not have simple answers, and different cultures, philosophical traditions, and ethical systems will provide different responses. But the very fact that we are asking these questions is significant. We have moved from abstract speculations about the possibility of life in space to a concrete case that requires practical solutions. Mars is no longer a hypothetical possibility. It is a reality we are observing, a changing planet that may be on the verge of transformation. And our next steps, the scientific missions we send, the decision of how to interact with the discovered processes, the biosafety protocols we develop, will all set precedents for a future when humanity encounters other forms of life or pre-biology in space. The story of Comet 3, I Atlas, and the Martian anomalies is not over. It is just beginning. The rover is en route. Mission Genesis is under development. Observations continue. In the months and years to come, we will learn more. The picture will become clearer. Perhaps we will receive final confirmation of the biological nature of the processes. Perhaps we will find a non-biological explanation that will nonetheless open up a new field of chemistry or planetology. Perhaps we will remain in uncertainty, acknowledging that some questions do not have unambiguous answers with the technologies available to us. But regardless of the specific outcome, we have already changed. We learned that the universe is full of surprises, that our expectations are often too narrow, and that nature is more inventive than any theories. We realized that the cosmos is not static. It is dynamic, full of processes that occur on timescales from seconds to billions of years, from atomic sizes to galactic distances. And we recognized that our knowledge is negligible compared to the volume of the unknown, that every answer gives rise to dozens of new questions, and that the path of knowledge is endless. Mars today is a riddle wrapped in a mystery, hidden beneath layers of red dust. But this riddle is accessible to our instruments. This mystery can be unraveled by our methods. This dust can be studied by our robots, and perhaps someday by our hands, when the first humans step onto the surface of the red planet and see with their own eyes what we now observe only through the prism of data and models. And when that happens, when an astronaut bends down and takes a sample of Martian soil in their hand, from the zone where the processes triggered by Comet 3, I Atlas occurred, it will be a moment connecting the past and the future, a moment when humanity directly encounters the result of interstellar exchange with matter that has traveled light years and changed a planet. In that sample, in its molecular structure, in the patterns of its crystals, a history will be encoded, the history of a long-vanished world, the history of a long journey through the void, and the history of awakening on a new planet. And we will learn to read this history, to decipher its chemical language, to understand the messages that the universe sends through time and space. The sun is setting over the Martian plains, painting the sky in shades of blue and violet, the reverse of terrestrial sunsets due to the different atmospheric composition. Shadows lengthen, and the temperature drops at a speed unimaginable on Earth. In the zone of activity, the processes slow but do not stop. Beneath the surface, protected from the night cold, they continue, maintaining warmth, releasing molecules, and changing the planet, atom by atom, molecule by molecule. And orbital stations, flying over this zone, record a faint infrared glow, a signature of heat, a signature of activity, a signature of something that is happening in the darkness of the Martian night. What is it? Life, pre-biology, complex chemistry, or something we don't yet have a name for? The answer is somewhere out there, in the red dust, in the frozen brines, in the cracks of ancient rocks. The answer awaits us patiently, as it has for 4 billion years, and we are moving toward it slowly, cautiously, but relentlessly, because that is what humans do. We ask questions, we seek answers, we explore the unknown, and sometimes in the process of searching, we find not what we were looking for, but something greater, a new understanding, a new perspective, a new sense of our place in the vast, complex, astonishing universe we call home. Mars is silent, but its silence is full of meaning, and we are learning to listen.